technologies. There are all sorts of different technologies that deal with computer graphics. In this course, we're going to look at some of them. For example, some of you will be programming some JavaScript code. In 2D, if you're rendering 2D computer graphics, then you can use the HTML canvas element functions in JavaScript to draw different 2D shapes. And then your web browser is just going to render them. Some of you will be programming some C++ code. So in the C++ branch with 2D, we'll be using the Allegro game library. And although it's a game library, it has some very good functions for computer graphics as well. Of course, in this branch, you will compile an executable program, and then that will render or communicate with the GPU, and then the GPU renders the result to your screen. In the 3D technologies, in the JavaScript branch, we're going to use 3JS. So 3JS uses WebGL, and this also runs in the web browser. But why are we using this 3JS is because programming pure WebGL can be a bit tedious, and like I mentioned in the previous video, there are common operations that people do when they implement computer graphics. And 3JS has this nice object-oriented structure that allows you to use these algorithms and put together your scene and implement your own algorithms in a way where you don't have to do a lot of like low-level code. In the C++ branch, it's gonna be more about working with OpenGL, but we'll also use some libraries like GLM, which is a maths library. So computer graphics, as you'll see in the later material, is largely about math. So it's useful to have a library that does some common like vector math matrices for you. And this GLFV for different windows and rendering things in a window. Now this OpenGL and WebGL that we have talked about. So those are APIs that allow you to communicate with the GPU or GPU drivers. So let's say this OpenGL, it's used to send different calls to the GPU. It exposes an interface, or actually it defines an interface, and you can actually use this interface with different languages, in C++, Java, Python, it's there. And this interface or these functions allow you to configure the GPU to render what you want it to render. Same thing with WebGL. So WebGL is based on OpenGL, actually OpenGL embedded systems. We'll talk about this more in a minute. But this is very similar to OpenGL, except that it runs in the web browser. So in the web browser with JavaScript, you have access to an API that allows you to communicate with the GPU and render 3D graphics on the screen, just like you would do in a game or a C++ program. Now, both of those use this GLSL, this graphics library shader language. And besides just the different calls you send to the GPU, you have to also send a piece of code. Actually, two pieces of code. And this code is programmed in GLSL. And it's very similar to the C language. And these two pieces of program code manipulate the different vertices of the geometry you send to the GPU and the different pixels on the screen, or as we like to call them, fragments. And to be perfectly accurate, fragments are a bit smaller than a pixel, but let's not go into that. In this case, you can think about fragments as the different pixels on your screen. So if you look back at the pipeline, so we had the CPU, where you define your data, you send it to the GPU, and then GPU is going to process that data. So if you have geometry, and we'll talk about geometry later in more detail, then vertex shader is the first thing that is run on the vertices. And you have to send along with the data a GLS code for the vertex shader. The other steps here are also configured, so you can configure these different culling and clipping modes, visibility test blending, and we'll see all of that throughout the course. And maybe the most important thing you send is the GLSL code for the fragment shader. Nowadays, a lot of the computer graphics algorithms are actually implemented in the fragment shader. In the old days, it used to be pretty expensive to do larger calculations per fragment because there was lots of fragments, the screens are big, and the GPUs were not that powerful. But nowadays, because GPUs are more powerful, you can do a lot in the fragment shader. But just remember that for all of these steps, you have different configuration that you send or different calls that you can make to configure different states in the GPU. And you have to send a vertex shader code and a fragment shader code. And we'll see this in the practice sessions as well. Now, if you talk about OpenGL, we can look at the history a bit. So here's an OpenGL API family tree. It's a bit old slide from the Kronos group. So Kronos group is the association that develops these OpenGL, WebGL, Vulkan, different open standards. And because we'll be using WebGL and OpenGL in our course, then it's useful to understand like what has happened with those APIs and what are the versions that we are using, or what are the latest versions based on. And there are some differences between WebGL 2.0 that we'll use and well the latest OpenGL versions. The most notable differences come because WebGL is kind of based on OpenGL embedded systems, which is based on like these middle versions of OpenGL. But the situation is a bit more complicated because WebGL 1.0 was based on like a very early version OpenGL 2.0, and some of the things have like passed on through this chain here that are not that common in the regular OpenGL anymore. But you'll see all of this in the practice session. One thing to know about this history is that in the very early versions of OpenGL, it was kind of this fixed function 3D pipeline. So you didn't have these shaders and you couldn't really do the things you can now. And at some point in around this OpenGL 3.1 era, things changed a lot in the OpenGL API. This is why there are some differences between like WebGL, which some of it is based on like the earlier OpenGL versions and some of it on the newer versions. And if you Google a bit, you see that OpenGL isn't really in development anymore, or like the last stable version is pretty old by now. So you might be wondering like why are we learning this OpenGL, like I've heard about these new technologies like Vulkan and the WebGPU and different new technologies, and maybe even this WebGL is a bit outdated. One of the reasons is that OpenGL has a lot of different learning materials. It conveys the pipeline and what the GPU does quite approachably, so it's not overly complicated. And a lot of different technologies still use OpenGL. And while there are newer APIs that might be taking over, usually people think like that OpenGL isn't going anywhere. So, for example, if you search about this, like in this Reddit thread, is OpenGL considered to be deprecated, old, unused? Then a few years ago, this person answers no. So, and they also point out that there is this difference in the modern OpenGL like 3.2 plus. So this is absolutely not outdated. But yes, the legacy OpenGL 1 to 3.1 fixed function pipelines, that certainly is. But there is even like a more recent thread that questions, is OpenGL still worth learning in 2023? And one of the answers is that like if you want a highly accessible and reasonably open source way of learning 3D programming, then yes. And this is why we're using it in this course. Now, in this video, you should understand like the different technology stacks. So we differentiated between like 2D stacks and 3D stacks. And of course, there are many more ways and stacks that you could use. But these are the ones that we just use in this course. Then the different libraries that are used with the APIs. And the differences in like JavaScript and C++ branch. Like one is rendered in your browser, another is a built executable. Then we looked at the OpenGL family tree. So this WebGL 2.0 is based on these OpenGL embedded systems and the core versions. And then we discussed like, is OpenGL dead? It's not dead. It's very accessible for learning. And one of the other key points is that the knowledge you learn by programming graphics with OpenGL is easily transferable to other technologies. So if you consider learning Vulkan that needs 1,000 lines of code to draw a triangle, then you are better equipped to understand what those 1,000 lines of code would do.